Hello students, now we will be solving memory-based questions of GATE 19. For more video solution on GATE 19, subscribe to our channel and don't forget to click bell icon for instant notification.
Hello student, my name is Devashish Chakravarti and today we are going to solve a question that came in the 2019 GATE exam in the set 2, that is in the afternoon session for mechanical. The question is from fluid mechanics and the topic is fluid machines. So let's see, the question is in front of you. Let's read the question together. An idealized centrifugal pump. An idealized centrifugal pump. Blade outer radius is equal to 50 mm. So they have stated that there is an ideal centrifugal pump and the outer blade radius, that is the outer blade radius, it will be more clear when I will draw the image. The outer blade radius is 50 mm. Now the question is, it consumes 2 kilowatt power. As we know that turbines produce power, the turbines produces power, whereas a centrifugal pump will consume the power. The pumps consume power and turbines produce power. Okay, so let's see. Consumes 2 kilowatt power while running at 3000 rpm. They have given the rotational speed, that is 3000 rotation per minute. The entry of fluid into the pump is axial. So at this point you should pay attention. The entry of fluid into the pump is axial, that is the flow is entering axially along the axis of the pump, and exit from the pump is radial, and the exit from the pump is radial with respect to impeller, Then mass flow rate through the pump is. Now they are asking what is the mass flow rate. So first thing, that how can we solve this problem? So even if you are not familiar with the concept of pump, even then we can solve this question just by reversing our concept of centrifugal turbines. As we know that in centrifugal turbines, the power produced is rho QGH. The power produced is rho QGH. Similarly, in the case of pump, the power consumed will be rho QGH, where H is the, in case of the pump, H is the head given to the fluid by the impeller. Consider this, that in case of turbine, the water gives a head to the impeller. In case of turbine, the water gives energy to the impeller. And energy per unit weight is head. So in case of turbines, the water gives a head to the turbine. In case of turbines, the water gives a head to the turbine. Whereas the reverse happens with pump. In pump, the impeller rotates and it gives energy to the water. The impeller will rotate and it will give energy to the water, and energy per unit weight is head. So in case of pump, the head is given to the fluid. Okay, now let's see how to proceed with this question. For your convenience, I am going to solve this question using the concept that we have learned for turbines. आपको ताकि आसानी हो और ताकि आपको नया कंसेप्ट सीखना ना पड़े, इसलिए इस क्वेश्चन को हम करके देखेंगे कि टर्बाइंस के कंसेप्ट को ही कैसे हम पलट करके इस क्वेश्चन को सॉल्व कर सकते हैं. तो देखिए, लेट्स सी हाउ टू सॉल्व दिस वन. वी नो दैट द हेड ऑफ द टर्बाइन इज गिवन एज, लेट्स से H turbine is given as VW1 into U1 minus VW2 into U2 by G. So the power produced by the turbine is given as P turbine is given as rho QG into H, where H is this value, rho QGH, where H is this value, H of turbine. Simplifying this equation, we get P of turbine is equal to rho Q into VW1 U1 minus VW2 U2. Yeah, that's it. So this can be written as mass flow rate into VW1 U1 minus VW2 U2. Okay, these are very known formulas. These are the formulas for the case of turbine. That is, in the case of reaction turbine, Francis turbine, these are the common formulas. Now let's see how to use the same formulas or make some little changes to solve it, the pump question. So okay, So this head of the turbine is basically the energy or the head that is given to the impeller. This head of turbine is basically the energy given to the impeller by the fluid. That is, the fluid is giving energy to the turbine. The fluid is giving energy to the turbine, and this is the H of turbine, that is head of turbine. That means the energy given by the fluid to the impeller per unit weight. The energy given to the impeller by the fluid per unit weight. So this is the H of turbine. Okay. In case of pump, इसका उल्टा होता है. In case of pump, the reverse happens. In case of pump, the impeller gives head to the water. That is, the impeller gives head to the water. So in case of pump, this becomes nothing but, because उसका उल्टा होता है ना, सिर्फ इसलिए एक माइनस लगाना है. Just because the opposite happens, we are going to add a minus. That's it. That is VW2 U2 minus VW1 U1. And then this becomes power of pump. That is the power given to the pump. The power given to the pump, it becomes, so which is essentially minus plus. Just add a minus. सिर्फ एक minus लगाना है. Plus and minus. So now we have the equation for the pump. The power produced by the pump. Write down this equation. This will come in handy next. Let's see how to proceed further. So let's draw one of the blade of the impeller of the pump. So let's say this is the blade. Okay. This be the entry. This be the point of entry. And this be the point of exit. Entry is from this side. Exit is from this side. As usual, for entry, we will denote it with 1, and for exit we will denote everything with subscript 2. So now let's see what happens. In the question it is given, read the question. The entry of fluid into the pump is axial. The entry of fluid into the pump is axial. So what we mean is, consider this. This is the impeller. This is the impeller. Now this is the blade. How they are arranged? Consider this diagram first. This is the impeller. This is the impeller. And these are the blades. These are the blades. I am considering only one of the blade. Let's say this blade is this one. Okay, so I am considering only one of the blade. This one is the entry for fluid. And this is the exit. That is water enter from here and exit from here. Now see. They have given in the question that the flow entry is axial direction. So basically what they are saying, the directions I must define. This direction is radial. This direction is along the radius. This direction is along the radius of the impeller. So this is radial direction. Similarly, this direction is tangent to the impeller. This direction is tangent to the impeller. So this is tangent. This is the tangent to the impeller. The axial will be, as you might have guessed, perpendicular to this board. The axial direction will be perpendicular to this board. That is in and out of the board. In and out of the board. That will be the axial direction. So definitely I cannot draw the axial direction velocity triangles on the board. I cannot draw. So, but we don't even need to draw this. Consider this. Let me write this equation again. Okay. So now see. If the water that is entering the pump, is axial in direction. The water that is entering the pump is axial in direction. One thing that I can confirm, one thing that I can say is, there will be no VW1. Where VW1 is the swell velocity. VW1 is the swell velocity, which means the component of V of entry, the component of entry velocity, in the tangential direction. What is VW1? What is swell velocity? The well velocity. What is well velocity? VW1. VW1 is nothing but the component of absolute velocity in the tangential direction. The component of absolute velocity of water in the tangential direction. In the tangential direction. That is in the direction of u. If the impeller is rotating like this, let's say if the impeller is rotating like this, if the impeller is rotating like this, then the u will be along this direction. Let's say this is u. At any point, u will be along this direction. This is u. So basically, u is in the tangential direction. U is in the tangential direction. So Vw1 or the will velocity is the component of jet velocity or the component of velocity of water, absolute velocity of water in the direction of, in the tangential direction, in the direction of u, in the tangential direction. So of course, if the water is entering in the axial direction, if the water is entering in the axial direction, that is perpendicular to the tangent, perpendicular to the tangential direction, then the Vw1, the component of this velocity, the component of this velocity along the tangential direction, the component of this velocity along the tangential direction will be 0. The component of this velocity along the tangential direction will be 0. So I can clearly say that Vw1 is going to be 0 just because the flow is entering in the radial direction. Clear up to this part? Now let's see. At the exit, they have mentioned in the question, exit from the pump is radial with respect to impeller. With respect to impeller. This is the most important part. With respect to impeller. So as they are saying with respect to impeller, what they mean is VR, the relative velocity. With respect to impeller, वो कह रहे हैं कि with respect to the impeller. तो जब impeller के respect में बात होती है तो उस velocity को हम बोलते हैं relative velocity. Relative velocity. तो इस केस में जो relative velocity है, the relative velocity that is radial in direction. The relative velocity is radial in direction. Very well. This is the, let's say this is the relative velocity VR2. The relative velocity is radial in direction. As I had mentioned before in this diagram, this is the radial direction. This is the radial direction. So the VR2 is basically in the radial direction. This is VR2. VR2 is in the radial direction. Okay. Now let's see. I had assumed that the blade is rotating in clockwise direction. So let this be U2. The blade is rotating in the clockwise direction. So this is U2. Complete the velocity triangle. So this is V2. V2 is the absolute velocity. V2 is the absolute velocity. So this is V2. This is VR2. The VR2 is the relative velocity with respect to the impeller. The relative velocity of water with respect to impeller. And they had given in the question that the velocity of exit is radial with respect to the impeller. So that means the velocity of exit is radial with respect to the impeller. So that is, they are talking about VR2 and they are saying that VR2 is in radial direction. U2 is in this direction. I had assumed that this impeller is rotating in the clockwise direction. So along the tangential direction, that is perpendicular to the radial direction, along the tangential direction, I am taking U2, and so this is the VW1. Okay? Sorry, this is V2. This is the velocity at the velocity of water, absolute velocity of water at the exit. This is U2, the tangential velocity of the blade, and that is VR2. Okay? Now the last important point is, what should be VW2? What should be VW2? See, in this triangle, VW2 is basically the component of V2 in the direction of U2. The component of V2 along the tangential direction. So, from the triangle you can see that VW2, the component of VW2 in the tangential direction is going to be U2 itself. The component of velocity, the component of absolute velocity in the tangential direction is going to be U2 itself. That is, if I am assuming this as alpha 2, so what I am saying is V2 into cos alpha 2 is equal to U2 only, and this is treated as VW2 is equal to U2. Okay, so now we have simplified this equation quite a lot. So let's substitute the final values and see what it comes. I hope you have understood this. And now let's just put the values in the equation. So now we can say that power produced to the pump was given, but it is PUMP, power produced to the pump, is equal to what we are left with, VW2 into U2, and we have stated that VW2 is same as U2. Basically this is U2 square, and this component is 0, so basically this is what it means. Now let's see. Now in the question they had given the rotational speed, that is they had given n is equal to 3000 RPM. Now we can simply convert it. We know that U2 is equal to pi d2 n by 60. U2 is pi d2 n by 60, and diameter, that is the outer diameter. U2 is the at the exit. U2 is the tangential velocity at the exit. So d2 is going to be the outer diameter. As d2 is the velocity, tangential velocity at the exit, that is at the outer side. Similarly, d2 is the diameter at the exit. That is, d2 is the diameter at the exit as the outer side, the outer diameter. That is, they have given as 50 mm. d2 they had given as 50 mm. Substituting this value, we will get U2 is equal to 7.85 meter per second square. 7.85 meter per second square. 7.85 meter per second square. Just substitute it. Power they had given that the pump consumes 2 kilowatt. The pump consumes 2 kilowatt. So the power is 2 into 10 to the power 3 is equal to mass flow rate into 7.85 square. So this will give you the result. M is equal to 32.42 kg per second. 32.42 kg per second. This is the answer. This is the answer that they were asking. Hope you have liked this video. Please share it with your friends. Thank you.